Okay, how do you find a linear model for a set of paired numerical data? How do you evaluate the goodness of the fit? That's what we're going to look at in section 4.9. Okay, so we've been looking at data a little bit. Here's a census of 30-year-old females. 1970, there were 29.2 million. 1980, 31.3. 34 in 1990, 36.5 in 2000, 38.2 in 2010. First, we need to identify the independent and the dependent variables. Obviously, the number of females is not deciding the year. Okay? Time generally is our independent because time doesn't get affected by conditions. So we could put T over here in our X column. Now, it's not going to make a lot of sense to write 1970, 1980. I think it's easiest to do these saying how many years from 1970. So years from 1970. And we could list them as 0, 10, 20, 30, 40. Okay. And then f of t, the function of t, 29.2, 31.3, 34, 36.5, and 38.2. So we make a t-chart, then we go ahead and we make a scatter plot. Fit it to your data. This goes 0 to 40, and I have 1, 2, 3, 4, 5. I can just go ahead and go 0, 10, 20, 30, 40. That fits well enough. You don't want it too squeezed or too spread out. Now going up this way, I went ahead and put a break. This is called a break in the data, showing that you're not going to go up by the same amount as you do up in here. So if we go 29, 38, we have 1, 2, 3, 4 squares. We could probably go 30, 32, 34, 36, 38. All that I did is I took the difference in there. This is almost at 30, that's 38. And I divided it by 1, 2, 3, 4. 8 by 4 is 2, so I just counted by 2's. And this is ages. Okay? Now we would go ahead and plot these. At 0, 29.2, about there. 10 would be 31.3. And I highly suggest that you use graph paper. I don't have boards that have the grids on them here at home. 20 is 34. That's the only reason that I don't. And if you don't have gridded paper, then you've got to just sketch it out right now in your notes. 30 is 36.5. 40 is 38.2. And we can see that we could draw a line there, preferably with a ruler. I seem to not have a ruler out here, so I'm going to do my best. Draw a line here that balances the number of points above and below the line. You don't want to necessarily draw it through any points. You want to just balance to get them as tight as possible in there. So I usually set my ruler on edge and really line it up where it's halfway between all the points. Okay, following the trend. So here's an example of that graph that I drew earlier. And we want to now find the line of best fit. So on that graph, we want to look at it, and we can see that the point that hit on it was at 20. We had a point on there at 2034, and then again at 30 another point hit, and it was 36.5. So what I do is I find the slope, just like you did with the function Munchkin game. It's 2.5 over 10. 2.5 divided by 10 would be 0.25, so that's your slope. So we go y equals 0.25x plus b. Now I would go ahead and plug in one of these points for x and for y. Since 34 is rounded off and even, I would use it over the other point. So 34 and 20. Now we can solve for b. 20 times 0.25, well 10 times 0.25 was 2.5. 20 will double that, so it'll come out being 5 plus b equals 34. We subtract 5 from each side, and we find 29 equals our b value. So for our line, we come up with the line of best fit being y equals 0.25x plus 29. Now I will tell you, there might be 30 different lines of best fit in a math classroom. So don't get yours and think that it needs to be identical to somebody else's. Be able to reason how you did yours and show all the work. So that's our line of best fit. Now to evaluate our line of best fit, we look at residuals. Residuals are the difference between the actual points and the points on the line of best fit. So if we zoomed in here and just turned this sideways and just looked at how the points are fitting on it, that's when we would get these residual plots. We're just looking at the line of best fit and how far the points are from it. We're doing like a close-up. If the residual plots show that the points are real close to the line, then the residual is that it's suitable and strong, it's random, and it's a tight fit. Now, if the points end up being real far spread, but they're still random, then we say it's suitable and weak. They're random and loose fit. But if we find that they're not random, that they might fit a different pattern, we should probably turn to the fact that it's not suitable. And that might be a different function rule rather than linear. Line of best fit that we just figured out was 0.25t plus 29. So now we want to take what the actual points were and plug in what points we get with our line of best fit and then discover the residual. It's easiest to grab a calculator to do this, but all that we're going to do is we're going to plug in the values into this equation. So right here, we can go ahead and we can plug in when we have 0 in the equation, 0.25 times 0 is 0, so it'll be 29. Now, to get our residual, we just subtract the actual minus the predicted, or the line of best fit, and we get a plus 0.2. Okay? Now we'll go 10 in there. So 0.25 times 10 plus 29, 31.5. So when we subtract that, this time we get a negative 0.2. 20 times 0.25 plus 29 equals 34. So that one's right on. We have a 0 there. 30 times 0.25 plus 29 equals 36.5. Another 0. And 40 times 0.25 plus 29 equals 39. So here we have a negative 0.8. So now we come over and we actually plot these. Okay, so our first plot is plus 2, right there. The next one is at -2. The next one is at 0. The next one is at 0. And the next one's at -0.8. So that's how our residuals look. Pretty good. These two are right on the line. This one, it's a little bit low. I would almost think that that line could be shifted down just slightly to get a better fit. Remember, you don't have to be going through the points. It's better to have a balance above and below. Okay, but that's not a bad fit. Not a bad fit at all. Okay, one last thing. With data, you're going to be asked to interpolate predictions and extrapolation with predictions. Let me explain what that means. Interpolation would be if I ask you, how many women do you think there might have been in 1975? And in predicting that, you could say, well, 1975 is only 5 years after, and you could come up here and hit your line of best fit. You could give me a pretty good idea and probably a pretty close estimate, and that is called interpolation. Because interpolation is within the data that you already have. It's inside. Now, extrapolation, just like exit, it means it's on the outside of it. That would be if I were to ask you, how many females do you think there will be in 2040? You would have to go clear off your graph, or even 2015. You have to go beyond your data and extend your lines out and predict. So it's not as accurate to extrapolate as it is to interpolate. Okay? So we'll see you in class.